I've got the Nintendo 64 games on the NSO expansion pack, and since I did not play on the original console, I thought it was the time to play them like they were intended to. I'm Rob, and this is how I designed my own adapter for using Nintendo 64 controllers on the Switch. It all started when I was convinced to get the NSO expansion pack with the Nintendo 64 games, which I'm not particularly nostalgic for, but still thought it was a good opportunity to do something with a controller I had lying around. Thus, I started to work on an adapter to translate the data from the controller to the Switch. I'm aware there are projects and products with the same purpose, but I wanted to do it my way, since I enjoy trying to figure out these kind of things myself. More than the games, really. My hobby is building weird stuff. For this project, I used an STM32F4 microcontroller, which I am comfortable with, they're pretty fast, and really nice to debug. To anyone who isn't familiar, a microcontroller is a programmable microchip containing a processing core, memory, input and output peripherals. It's kinda like a simple computer in a really small package. The microcontroller is programmed to decode the information from the joypad and then send it to the Switch. Since I needed to get the Switch to recognize the controller, I could try using USB or Bluetooth, although I chose USB because it's usually simpler. Because of that, the microcontroller I'm using has a USB peripheral, which means it can handle most of the protocol by itself, while I just have to worry about the data. I won't dwell too much on how USB works, because it would take a long time, but a nice starting point would be the USB in a nutshell write-up by Beyond Logic. For our intents, it suffices to know that USB devices report their information to the USB host during a process called enumeration, using descriptors. These descriptors contain information such as what is the device, who made it, the USB version, how it can be configured, etc. Then, if our device reports similar descriptors as those of a supported USB controller during enumeration and keeps sending periodic data like one, the console will have no problems to understand it. The more common USB descriptors are device, configuration, interface, and endpoint descriptors. These are defined once in the code. For example, this is the device descriptor. Besides, this will thankfully be an HID class device. Thus, we will also need to inform an HID report descriptor, which tells the USB host how to decode the package data that we send every cycle. This descriptor tells the host about the structure of the packets that will be sent. In this case, how the data containing the state of the buttons and the joysticks is organized. Then, we update the controller state periodically with HID reports. In the given report descriptor, the HID report is 8 bytes long and has the following structure. The first 2 bytes contain the button data. If a bit is a 1, the corresponding button is pressed. The third byte has the D-pad data, but each direction, including the diagonals, is encoded as an integer from 0 to 7. Then, there is access data for the 2 sticks, which is a value from 0 to 255, with the resting position being around 127. The last byte is a vendor-specific field, and I got away with simply ignoring it. After a few tries, I got to adapt an example code by the microcontroller manufacturer and program my own USB device with the configuration needed, which was acknowledging my computer as a USB HID joystick. Next, I needed to decode the N64 controller signal and send the data as HID reports. Now that we have USB working, let's have a look at the Nintendo 64 controller protocol. There are 3 pins in the controller connector, 2 for power and 1 for the signal. The controller uses a bidirectional proprietary serial protocol called JoyBus, or sometimes simply referred to as one wire. It won't send the signal by itself, and needs to be polled by the console with a request, so it can respond with the button data. Because there is only a single pin for communication, that can only send or receive at once, it is a half-duplex serial protocol. The serial data, either from the console or the joypad, is encoded as a series of pulses. While every symbol has a 4 microsecond period, ones are encoded as 1 microsecond low, 3 microseconds high pulses, and zeros are encoded as 3 microseconds low, 1 microsecond high pulses. Let's see this in practice. The console signals the read to the controller with a 1 command, which looks like this. Additionally, after each request or response, there is an always one stop bit. The duration of this stop bit, for some reason, is only 3 microseconds and not 4 like the data bits, which complicates things a little. After the request, the controller replies with a 32-bit plus stop bit response, containing the button and joystick data. For buttons, a logical 1 represents the button as pressed, like the start button in this example. In this logic capture, we can see the request and the response for a controller read, including the stop bits. The software is called PulseView, which is a graphic interface for SIGROC. Both are free and open source and can be used with simple logic analyzer boards like this one. It's been very helpful when I was debugging the JoyBus protocol, and I do recommend it. The 32-bit or 4-byte response of the controller can be decoded as the following. The first 2 bytes have the button's states. A 1 means that the corresponding button is pressed. On the other hand, the last 2 bytes are the joystick's X and Y axes, encoded as 8-bit choose complement values, that usually stand between -80 and 80. Now that we understand the protocol, there's still the matter of making the microcontroller decode all this. Using an input pin, we could check its state at 4 microsecond intervals, starting right in the middle of the symbols. That is, detach the start of the data, wait 2 microseconds, read the input pin state, wait 4 microseconds, read the input pin again, wait 4 microseconds, read the input pin again, and so on. As a naive first try, this worked somewhat, and while I still got a response from the controller, it could not be correctly decoded. This happened because while the microcontroller seems to be waiting, interrupts, in this case system timer, and USB host requests, take the CPU away from the waiting to execute these urgent tasks. When it comes back to waiting, the timing, which is critical, is all messed up. Then I try to program a timer peripheral, that is, timing hardware available on the microcontroller, to do the reading via interrupts. But since the controller communicates at a high frequency of 250 kHz, the microcontroller needs to service the interrupt, including switching context, and reading the input pin in less than 4 microseconds, which is a bit too much to ask of most microcontrollers. It probably could be done with a bit of assembly wizardry or using another timer mode, but later I found a more efficient way. There is this write-up by QWERTY detailing how they got to read the Nintendo 64 controller using the UART peripheral of a PIC microcontroller. For this, they used the resistor and a diode to tie both RX and TX pins of the UART together to the data pin of the controller. In this case, the STM32's UART already has a one-wire mode, which allows sending and receiving using a single pin, without extra components. The UART, usually simply referred to as serial, is a protocol for transmitting and receiving data. This is a typical communication for microcontrollers, and is used by a handful of integrated circuits as a means of exchanging data. This is a timing diagram for an example of a classic UART packet. I mean classic because there's 8 data bits, no parity bit, and a single stop bit. This is usually called 8-in-1 configuration. Considering an idle high UART, the start bit is always 0. The data bits are the information being sent, so they can be either 0 or 1. And finally, the stop bit is always 1. Now the interesting part. QWERTY did the trick of reading 2 bits of the N64 controller into 1 byte of the UART protocol. Although the timing is not exactly right, it works fine. Microcontrollers are getting faster nowadays, so I figured out I could get the exact timing if I used the word of the UART as 1 bit of the controller, by running it at 3 MHz using a 9N2 configuration, supported by the UART hardware on the STM32. Taking into consideration that the start bit is already logic low, and the 2 stop bits are logic high, reading bits 4 or 5 of the UART package would indicate if the N64 bit represented by the package was a 0 or a 1. Therefore, I programmed the routine using the HAL library, and it worked out fine, except I was losing the first button, A. Remember that the stop bits are 3 microseconds and not 4 as everything else? The joypad started sending the response before the microcontroller could enter receiving mode, since it was still transmitting the stop bit. Manually writing the N64 stop bit into the UART registers without the library and switching to receiving mode before the completion of the stop bit transmission made everything work perfectly. As I said before, I only needed to check the 5th bit of each UART word to know if that bit is a 0 or a 1 in the JoyBus protocol. Having both the N64 controller protocol and USB figured out, I only had to translate the button and joystick data to USB AGID. Now let's see how we can use the data from the controller to prepare the AGID reports. I programmed the microcontroller to periodically get the latest controller state, which is then used to update the AGID report to be sent to the host. However, as we can see, the data layouts are different, and there's some work involved. Some of the buttons are very straightforward, and are just copied from the controller structure to the model counterpart in the AGID report. For example, if button B is pressed on the controller, we also set the corresponding bit in the report. The Z button is copied to ZL, like the NSO mapping expects. The G-pad is not quite as simple. The controller represents each main direction as a bit, so diagonals are 2 directions pressed at once. The AGID report, on the other hand, expects the rotation value between 0 to 7, while 8 means nothing is pressed. Then we check the possible directions and write the matching rotation value to the AGID report. While modern controllers use analog sticks to control the camera nowadays, the N64 controller uses buttons. Thus, if a camera button is pressed on the controller, the right stick on the report is updated as if totally tilted to the corresponding direction. The X and Y joystick coordinates on the N64 controller are values between -80 and 80, although the range in the report is from 0 to 255. This is not a problem, since the position can be easily converted using this mapping equation. After all this, the N64 controller features are converted to a modern controller's counterparts. Still, there are a few improvements that can be made. Playing the N64 games on NSO without a minus button would be a pain. It is used to open the suspend menu to select another game or save and load states. I solved this problem by simulating the minus button using a combo of L, Z, and up, which likely won't be pressed in regular gameplay. While I was at it, I also did the same for the home and capture buttons. While testing, I noticed some inconsistency of the joystick limits. After power cycling a GNY controller a few times, the maximum and minimum values for X and Y changed every time. Also, the range on the fake blue controller was not correct, varying from -128 to 127, which means it is probably too sensitive when playing on a real Nintendo 64. I searched online, and it seems that the range of a GNY N64 controller may vary with time, and be dependent on wear. As a result, each controller may have a specific range. Because of this, I made the maximum and minimum values for each joystick axis, which are used to convert the position, self-adjustable. That way, the real limit of the controller will be mapped to the limit of a USB joypad. The limits will start at 40 and be updated whenever the joystick is moved beyond that. That means that with a few turns of the analog stick, the adapter will match the joystick range and correctly map the position to the USB range. In addition, by inputting a literal Konami code, the controller will enter an alternative mode in which the C buttons work as A, B, X, and Y, which makes the N64 controller more compatible with modern titles or SNES games. This concludes the microcontroller tasks, but I also designed a 3D printer enclosure for the adapter. The prototyping setup I had was not optimal, so I later switched to a smaller board, which already had USB-C, and started to work on a 3D printed shell. This was the first time I designed anything in 3D. and it made me make my mind about getting a 3D printer. I spent a lot of time on this project trying out new ideas for the shell, printing, and making adjustments to the designs. I decided to model the controller connector, which is proprietary, into the design. While the features are small, it works quite well despite being printed with an FDM 3D printer. The microcontroller board is held between the two shell parts, which keep it in place. The USB-C connector on the board is aligned with the hole in the cover piece. I tried snapping, locking, and press-fitting mechanisms for keeping the two parts together. In the end, I decided for using a screw, which worked flawlessly while keeping the design simple. That's it. It may not seem like it, but this was a lot of work. Don't know if I'm really gonna use this a lot, but it was a nice project that allowed me to expand my skill set to 3D printing, modeling, and even video editing. I've tested the adapter with genuine and fake controllers, and it seems to work quite well with either. Besides, I haven't noticed any input delay, and it feels responsive like using any USB joypad. Now I can play these classic games on my Switch with the original controller. Not only, but it also works on modern games, as long as the missing buttons or the camera are not needed. That's all I had to talk about. Thanks for watching. Check out the description if you wanna have a look at the code. This is Rob. Thank you for joining me. See you again soon. Bye bye.